Good morning, friends and dear student. It gives me immense pleasure to be here again for my favorite course, Engineering Thermodynamics. I am Dr. Dwivedi from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. I am in the process of Engineering Thermodynamics and I am in last module, that is module number 5 for BTech students. This module belongs to the heat transfer and gas compressors. I am in the process of heat transfer now. Before this, I have completed the introduction to heat transfer, conduction, convection and the radiation. I have already done. We have seen the Fourier's law, Newton's Coulom's law. We have already described the conductivity, coefficient of conduction, coefficient of convection H. We have also seen the radiation, Kirchhoff's law, that radiation heat transfer rate is directly proportional to the T to the power 4. Q dot radiation is equal to epsilon sigma as T to the power Ts to the power 4 minus T infinity to the power 4. We have also discussed about the black body. The black body is the body in which the emissivity and the absorptivity is 1, that is maximum. This we have discussed in my last class. So in today's class we will be doing some energy balance. We have to find out by the help of derivation of the energy balance for heat transfer, boundary condition and types, Newton's law of cooling, relation between K and H, that is conduction and convection coefficients. This we are going to discuss in today's topic. In the previous class, I have discussed about introduction to thermodynamic radiation. This radiation is depend on the temperature. If this is one body, it is radiating some heat, and another is here the body which is also radiating. If this T1 is greater than the T2, this is the T2 and this is the T1, so the heat will be emitted, and this heat is not depend upon the atmosphere. It is not depend upon the media. It is directly hitting to the surface, and the surface will be heated first. This radiation will only hit the surface, and as this temperature is high, this will go here, but this will not come here, and the net effect will be this temperature minus this temperature, and slowly this body will be heated. So this is the radiation. And here we have the Stephen Boltzmann law here. Then we have seen the absorptivity alpha. Then we have seen the Kirchhoff's law, and radiation and the heat transfer we have already discussed in our previous class. Please refer my previous lecture for full detail. Now we will see the energy balance. So the energy balance we will see for the element. The element size is delta x, delta y in this direction vertical, and delta z in this direction. This is the delta z, this is the delta x from this side, and if you see here, this is the x direction, vertical is y direction, and perpendicular to xy is z direction, and it is shown a single element. In this element, the qx is entering from this surface and leaving perpendicular to this. So if you see this x, the area perpendicular to the x is delta y into delta z. So always the area which is to be considered is a perpendicular to the direction of the heat flow, not in the direction. So the x will not be counted towards the x direction. That we will be very important. So here it is entering the Qx, leaving the Qx plus delta x. From here vertically it is entering the heat Qy and leaving the Qy plus delta y. For the z it is entering in this and leaving opposite to this, that is Qz plus delta z. So this is a small element, and in this the heat transfer we have to see the energy balance, how these things are taken place. For any energy balance, first we need to write that Q dot is equal to rate of heat generated per unit volume. Q dot is what? It is a rate of heat generated per unit volume, and volume V is equal to delta X into delta Y into delta Z. For this element, the volume is delta X, delta Y and delta Z. General thumb rule of any balance is input minus output plus generation is equal to accumulation. Means how much it is entering minus how much it is leaving plus how much it is generating. This generation will be plus or minus. It depends upon, if it is generating it is plus, if it is reducing it is minus. So input minus output plus generation is equal to accumulation. Means this accumulation is how much it is stored inside the element. Input means how much you are entering the heat. Output means how much it is the leaving, and G for the generator. This is a mantra of all energy balances in any engineering discipline. It is not only thermodynamics. Any engineering discipline, you have to use the same mantra for anything. So general balance for conservation of energy. We will take the conservation of energy. Just I have discussed, I think in second class, that we have the conservation of mass, conservation of momentum and the conservation of energy. Because here we are taking the conservation of energy because heat is energy and we are here finding the energy balance. So here we are taking the energy only. So here if you see Qx plus Qy plus Qz minus Qx plus delta x minus Qy plus delta y minus Qz plus delta z. This is the input Qx, Qy and Qz, and output is Qx plus delta y plus Qy plus y plus delta y plus Qz plus delta z plus Q dot. It is Q dot is a per unit volume, so we have to multiply by volume. So Q dot Qx, Qy, Qz is equal to, it is accumulation. Accumulation is stored, so it is a rho Cp dt by d capital T by dt. Here it is T is the time, it's a rate, and into volume dx, dy and dz. It is accumulation of heat per unit volume. This is the rate of heat generation per unit volume. So this we have to understand that these things are per unit volume. So Qx plus Qy plus Qz minus Qx plus delta x minus Qy plus delta y minus Qz plus delta z plus Q dot delta x, delta y, delta z is equal to rho Cp. It is a constant specific heat at constant pressure. Rho is a density, dt by dt. T small t is the time, delta x, delta y and delta z. Now we will see, now divide by the volume, that is delta x, delta y, delta z, and rearranging this thing. So all this Qx term we will have at one place, Qx plus delta x. So Qx minus Qx plus delta x divided by delta x, delta y, delta z. So this delta x, delta y, delta z, it is a volume, plus Qi minus Qy plus delta y, delta x, delta z, plus Qz minus Qz plus delta z divided by delta z, delta x, 1 by delta x, delta y. So everywhere, if you see these all things, they are the volume. So we are dividing by the volume, and here this volume was there, so it is only Q dot, and here also the volume will go off. Here we will get Cp rho dt by dt. We can rewrite this by putting the limits. If we are putting delta x, delta y, delta z is tends to 0, so limit value, then we can write in differential form. So here we can write del Qx, this one we can write del Qx by del x, 1 by delta y delta z plus minus del Qy by del y, 1 by delta x delta z, minus del Qz by del z, 1 by delta x delta y, plus Q dot is equal to rho Cp del T by del T. So here minus we are putting because it is the reducing side. The heat is reducing. So we have put here minus. So this is the model equation for this heat transfer. With this can we get the temperature distribution. So this is the basic equation for the heat transfer of the system. So with this equation can we get the temperature distribution. If we know the constitutive relationship between Q and the temperature, then we are done with to find the temperature distribution. So if we know the relation between Q and the T, so here we have the T, this is the T, and here we have the R, here we have the Q. So if we know this relation, we can find out the temperature distribution. So now we know that the Q is given by the Fourier's law. So this Qx is equal to Ax into Qx double prime. His double prime is a flux. This Q double prime x is equal to heat flux, and Ax is the area of this perpendicular to the x. So here we can write that Qx is equal to minus K, area is equal to delta y delta z, and here we know that Qx is equal to minus Ka dt by dx. So we are putting here the same thing. So here Qx is equal to minus K into A dt by dx. So here Q double prime is equal to minus K dt by dx. So we will get here Qx is equal to minus K dy dz del T by del x. Qy is equal to minus K del x del z del T by del y. Qz is equal to minus K del x del y del T by del z. We can substitute this in the previous equation, and then we will find out that del by del x inside the bracket K del y del z del T by del x 1 by del y del z plus del by del y K del x del z del T by del y 1 by delta x delta z plus del by del z K delta x delta y del T by del z 1 by delta x delta y plus Q dot rho Cp into del T by dt. So here we can see that if we take out the K in this, so K, and we will get del 2 and this delta x, delta y and delta z, it will be vanished. From here, if you can, you can see this and this, this and this, this and this, it will be vanished. So here K del 2 by del x square plus del square T by del y square plus del square T by del g square plus Q dot is equal to rho Cp del T by dt. So this we can write as a del square, this inside this thing. So here we can write that del square T plus Q dot by K is equal to rho Cp by K del T by T. So here we have divided by K. So we got here del square T plus Q dot by K is equal to rho Cp by K del T by T, where K by rho Cp is equal to thermal diffusivity, and it is alpha and its unit is meter square per second. So here this is the 1 by alpha here. So we got this equation that, and here is the Laplacian equation that del square T is equal del square T plus Q dot by K is equal to rho Cp by K del T by dt. So now we have to see that how we can sort out this. So here rho Cp is the capacity to store the heat, and K is the conductivity of the substance. So here equation which we got is partial differential equation. To make the partial differential equation complete, we need boundary condition. So we have to discuss the types of boundary condition. In the next slide, we are going to see that how we can solve this equation which we have got just now. So here we will see the types of boundary condition in thermodynamics. So here we have the first condition is constant temperature boundary condition. So in this type of, you can see this diagram here. So here T1 is the temperature, it is a constant at x is equal to 0. At x is equal to 0. So temperature is fixed at x is equal to 0. So T at x is equal to 0 is equal to T1. It is given the first condition that Tx is equal to 0, T at x is equal to 0 is equal to T1. And this we can give the example of a water geyser which temperature is constant and it is heating coil is fixed. So suppose one 500 watt, it is, if you switch on, it will give the 500 proportionate, it will give the temperature. It will not vary. So like these conditions are constant temperature boundary condition. Next is the constant flux boundary condition. In this we have the two sub categories. One is the zero flux boundary condition. So when we talk about the flux, we know that minus k dt by dx at x is equal to 0 is equal to constant. Means at this it is here at a constant it is given. Its no flux temperature is constant. So there is a no flux. So dt will be 0. So next is the boundary condition is non-zero constant flux boundary condition. So minus k dt by dx at x is equal to 0 is equal to q double prime s. It is a constant, flux is a constant. So third one is the variable flux boundary condition. So here minus k dt by dx at x is equal to 0 is equal to q double prime at the t. Means it is vary with respect to the temperature. Its functions local temperature, its variation as per the temperature. So how to quantify the flux? It is also called the convection boundary condition. So this one is also called the convection boundary condition. So we will see here the Newton's law of cooling. Similar to the Fourier's law for solid system, the constitutive relationship with heat transport of fluid and solid is given by the Newton's law of cooling as depicted in the figure. So here we have the slab. The slab temperature, the surface temperature is the Ts. Outside is some fluid. The fluid is a hot fluid. This is a hot fluid and it is moving with the temperature T infinity. So this T infinity is greater than the Ts. So here H is equal to transport coefficient between fluid and the slab solid applicable for two-phase system. So here it is a liquid and here is the solid. So this is the solid. So now flux at T, Q double prime T is equal to H, T infinity minus Ts at X is equal to 0, means surface temperature. So we can write this Q double prime, that is flux is equal to minus K dt by Tx at X is equal to 0 is equal to H, T infinity minus Ts at X is equal to 0. So the profile of the temperature distribution will be dt by dx will be dictated the profile and the flux. So this you can see the profile of the flux will be like this as shown in this solid. Here H, T infinity minus Ts will dictate in fluid. In this temperature is continuous variable. Both should be balanced, that is K and H. So in this condition both things to be balanced. So we will see here that These are the references which I have taken. That is P.K. Nag, Engineering Thermodynamics, Tata McGraw Hills, 4th edition, 2004. Eunice Senegal, Michael A. Bors, Thermodynamics and Engineering Approach, Tata McGraw Hills, 7th edition. Any questions you can ask to my email dwivedi@gmail.com. Also, I request to like and subscribe this channel. And if you want, you can give the comment. Thank you very much for the joining. Till then, goodbye. Please do watch my next lecture also.
Like, share and subscribe. Hit the bell icon for more updates.